The branch of physics that studies the motion of an object with no reference to the external agent that causes the motion is called kinematics. And we have three different types of motion that we study. The first one is translational motion. For example, if you have a car that is moving in a certain direction. Rotational motion, this could, for example, be a rotating ball. And we have vibrational motion. For example, if you have a mass spring system, mass attached to a spring, and the spring stretches and compresses periodically. So when we talk about these motions, we have a model in our mind. Basically, we're going to model all objects as particles, so we will be dealing with particle motion. And when we say it's a particle, that what we mean is a point-like object that has mass, but it has infinitesimal size. Okay, so when we study the motion in one dimension, and later on we're going to do also kinematics for motion in two dimensions as well. We have to define a few important physical quantities. The first one is position. Position we show with x or r, and it is the location of a particle with respect to a reference point. And the displacement, on the other hand, of a particle is defined as the change in position in some time interval delta t. So if we denote the position of the particle with respect to a reference point as x, then we have the initial position xi and final position xf, and we can show these as vectors, and the change in the position of the particle from x initial to x final gives us the displacement vector delta x. Now, we don't actually need to use these vector signs for these quantities in one dimension, because the sign of the quantities takes into account the direction. It's either in the positive direction or negative direction. But nevertheless, since in general we have to use these vector signs in order to show these quantities, and they are by nature vector quantities because they have a direction, I'm going to define this position and displacement as vectors to start with, even for one-dimensional motion. The distance traveled is the length of the path followed by the particle. So the particle travels a certain distance when traversing a path, and that distance that we travel is called the distance, and we show it with d. It's a scalar quantity, it's not a vector quantity. The average velocity of the particle will be its displacement divided by the time interval delta t. So mathematically speaking, we can say it's the displacement vector divided by the time it takes to complete the displacement. That is the average velocity of the particle. I show it with Vx here to show you that the motion is on the x-axis. It's a one-dimensional motion. As opposed to average velocity, we also have average speed. This is the total distance traveled which is divided by the total time interval. So it is the total distance traveled divided by the total time interval. So it is a scalar quantity. D is, because distance is a scalar quantity and time is a scalar quantity, d divided by delta t is the average speed of the particle. Okay, so for an example, we can consider a basketball player moves to the other team's basket at a distance L and returns back. So how much is the total displacement of this basketball player? Because the final position vector and the initial position vectors are the same, at the end, the basketball player goes back to the original position. The total displacement is zero. However, the total distance traveled is 2L, because there's a distance L that the basketball player has to travel to reach the other team's basket, and another distance L to go back. So total distance traveled will be 2L. Now, we can think about another example where we have the position of a particle plotted versus time. And you can see this particle is traveling from position A to position F following this path. So you can see that XA is 30 meters. So that is the position of the particle at the beginning at t is equal to 0. And XF is minus 53 meters. It's the position at time equals 50 seconds. The displacement delta x is the difference between xf and xa. It is minus 53 is final position. Initial position is 30, so minus 30, minus 83 meters. Because I'm showing this as a vector here, I should say that it is in minus I hat direction. So I could show this as minus 83 I hat in meters. So that is the displacement. Now, what is the average velocity of this particle? It's the displacement delta x divided by the time interval delta t. So over the time interval ta to tf, the particle goes from position A to position F with a total displacement of minus 83 meters. So minus 83 divided by Tf minus Ta, 50 minus 0. This gives me minus 1.7 meters per second. And because I'm showing these as vectors, even for one-dimensional case, I should denote that this is in minus I hat direction. What is the total distance traveled by this particle? Well, I have to look. So I started at 30 meters A. I went to position B. So the total distance I have traveled there is 52 minus 30, 22 meters. Then I travel 52 meters to position D, and then I travel 53 meters to position F on the x-axis. So 22 plus 52 plus 53, 127 meters is the total distance traveled. And the average speed of the particle is then total distance traveled divided by the total time it takes to complete the motion, 127 divided by 50, that is 2.5 meters per second average speed. So you can see the average velocity is minus 1.7 meters per second, minus 1.7 I hat meters per second, but the average speed is 2.5 meters per second. Now, in addition to these average quantities, we can talk about instantaneous velocity and speed. The instantaneous velocity Vx vector is the limiting value of the displacement divided by the time interval as the time interval approaches 0. So its definition is limit delta t approaches 0, delta x over delta t, which is by definition derivative. So it is the derivative dx dt. And we can find this for this motion between A and B, the average velocity. So it's the change in position xb minus xa, that's the displacement, divided by tb minus ta. That gives me the slope of line AB. So that is the average velocity. How about the instantaneous velocity at t is equal to 0? That is dx dt at t is equal to 0. For that, I have to look at the slope of the green line. So that is the derivative of this function x of t at t is equal to 0. So that gives me the green line. And you can see that this instantaneous velocity can be positive, which is the green line, can be 0, that is the red line. So at position B, you can see that the velocity becomes 0 because there's no slope. And it can also be negative, that is the purple line. For example, at position E, the velocity at t is equal to 40 seconds, the velocity is negative. Okay, so it all depends on the slope of the line x of t. Now, the instantaneous speed of a particle is defined as the magnitude of its instantaneous velocity. So this is completely different from the average speed. For the average speed, we have the total distance traveled divided by the total time it takes to complete the motion. But for the instantaneous speed, we have the magnitude of the instantaneous velocity. So it is magnitude of dx dt. Now, as a special case, we could have a constant velocity motion. So when you have a constant velocity motion, that means we have a constant slope in the xt plot. So from x initial to x final, it's a linear path in a time interval delta t. For this type of motion, the instantaneous velocity, which is the slope of this line, will be equal to the average velocity. They're both equal to delta x over delta t or dx dt. Because delta x over delta t and dx dt are the same, we have a single slope. So if I take the integral from x initial to x final of dx, that means I will be looking at, because Vx is equal to dx dt, dx is Vx dt, so integral from 0 to delta t, Vx dt. So the integral of dx from x initial to x final gives us delta x, which is x final minus x initial. Integral of Vx dt gives us Vx delta t, and you can see that this tells us delta x must be equal to Vx delta t. Well, delta x is equal to Vx delta t. You can see that from the slope here. So that means x final is equal to x initial plus Vx delta t. So in the xt plot, the slope gives us Vx, the intercept gives us at t is equal to 0, the initial position of the particle, and the final position is related to the initial position by x initial plus Vx times delta t for constant velocity motion. Now, if we also change the velocity of a particle in time, if it's not a constant velocity, but the velocity is changing in time, we say that the particle is accelerating. If it's increasing in time, we say it's accelerating. If it's decreasing, we say it's decelerating. So the average acceleration is the rate of change of its velocity. So basically, it is delta Vx vector divided by delta t. So it's Vx final minus Vx initial divided by t final minus t initial as a vector. So the dimension of acceleration is dimension of velocity divided by time, because we're dividing delta v by delta t, and velocity is dx dt, instantaneous velocity, which is length divided by time. So dimension wise, acceleration is L over t square, which is in SI units meter per second square. The velocity is meters per second and the position is given in meters. Now, the instantaneous acceleration, on the other hand, is the limit of average acceleration as delta t approaches 0. So it is the limit delta t approaches 0, delta Vx over delta t, which is the derivative of the velocity with respect to time. And since the velocity is related to position, it is dx dt, then we have for acceleration second derivative of the position vector with respect to time is its instantaneous acceleration. If you look at a velocity versus time plot, as you can see here, the slope at the final time, tf, gives us the instantaneous value of the acceleration at t is equal to t final. However, if I look at the change in velocity between a and b, delta vx, and I divide it by delta t, the slope of this blue line gives me the average value of the acceleration from the vt plot. Now, when velocity and acceleration are in the same direction, that means the velocity is increasing in time, we say that the particle is speeding up. And when velocity and acceleration are in opposite directions, then we say that the particle is slowing down because it is decelerating. Now, another special case is the constant acceleration motion. You can see here, acceleration does not change with time. So since acceleration is dv dt, and with a constant acceleration, this will give us the area under the acceleration versus time plot is the change in the velocity delta Vx. And since I have a constant acceleration, the way velocity changes with time is with a single slope. So it's going to be a linear change from Vx initial to Vx final, and it's going to be a linear plot. And since Vx delta Vx will be equal to Ax times delta t here, which I called t final, starting from t is equal to 0. And the area under the velocity versus time plot will give me the position, the change in the position, delta x, because we have basically velocity, instantaneous velocity is equal to dx dt. So if you calculate the area under the velocity versus time curve, you will get delta x. So the area under the acceleration versus time curve gives us change in the velocity. Area under the velocity versus time graph gives us change in the position. And since I have a linear change in velocity, and the position is going to be related to velocity by the integral v dt, you will find that the integral of at will be 1 over 2 at squared. So you will have a parabolic change in the position. So this will be our corresponding xt plot. Now let's take a look at this mathematically. Acceleration is dvx dt, so vx of t is going to be from integral from 0 to t ax dt. It's the area under at curve. So that's basically equal to delta Vx here, the change in the velocity. Now, because delta Vx is Vx of t minus Vx initial, and the area under the acceleration time curve is a times t, ax times t, we see that Vx at any time t is ax times t plus Vx initial. At t is equal to 0, we have the Vx value, Vx initial. Vx final is Vx initial plus Ax t final, and therefore you can see that t final is Vx final minus Vx initial over Ax. Now, since we also have Vx is equal to dx dt, delta x is the integral under velocity versus time curve. It's 0 to t, integral Vx dt. Because Vx is Vx initial plus Axt, so if I take the integral from 0 to t, this will give me Vx initial times t plus 1 over 2 axt squared is equal to delta x, which is xt minus x initial, or x at time t is x initial plus Vx initial times t plus 1 over 2 axt squared. So x initial is the value of the position at time t is equal to 0. For Vx average, because I have a linear plot for velocity versus time, I can simply calculate it as Vx initial plus Vx final divided by 2. It's the algebraic average of the two velocity values at the endpoints, since it's linear. And this will be equal to x final minus x initial divided by t final, because it's the change in position, the displacement divided by the time interval tf. So we have x final is equal to x initial plus vx initial times t plus 1 over 2 ax t squared, and for t final, I can substitute Vx final minus Vx initial divided by Ax. So basically, for Ax, I can substitute Vx final minus Vx initial over Tf. And I have another TF here, Vx initial TF. So you can see that X final will be equal to X initial plus 1 over 2 Vx initial plus Vx final times TF, which is the change in the position is basically the average velocity Vx average multiplied by TF. Okay, so then you can see x final minus x initial is 1 over 2 Vx initial plus Vx final multiplied with, if I substitute for t final, Vx final minus Vx initial over Ax, Vx final square minus Vx initial square is equal to 2Ax x final minus x initial, which tells us how the velocity is changing with position. So if you check this result for a zero acceleration, if Ax is equal to 0, this tells you that Vx final must be equal to Vx initial. That's what this equation suggests. And you have xt is equal to x initial plus Vx times t. So basically we recover the constant velocity motion situation. Okay, so to summarize, we have introduced kinematics for the one-dimensional case, and here we're only studying the motion of an object with no reference to who is causing the motion. There's no mentioning of the external agent. We talked about important physical quantities, the position, which is a vector, position vector, the displacement, which is the change in the position vector, another vector quantity. Distance is the total length of the path followed by the particle, which is a scalar. Average velocity is the displacement divided by the time interval. Average speed is the total distance divided by the time interval, which is a scalar. And we talked about instantaneous velocity, which is the derivative of the position with respect to time, dx dt. The instantaneous speed is now basically the magnitude of the instantaneous velocity. We talked about constant velocity motion, where you have the velocity versus time curve will be just a constant, but the position will be changing in time in a linear manner, so that x final is x initial plus Vx delta t. Then we introduced acceleration. This is the situation when you have a change in velocity in time. The average acceleration is the total change in velocity in a total time interval delta t, delta Vx over delta t. It's a vector quantity, and acceleration is measured in meters per second square, velocity in meters per second, and position in meters in SI units. The instantaneous acceleration is the derivative of velocity with respect to time, and we have distinguished two cases. If the acceleration and velocity point in the same direction, the object is speeding up. If they point in opposite directions, the object is slowing down. Then we talked about another special case, constant acceleration motion. That means the velocity is changing linearly with time, and that means a parabolic change in the position in time. And we can see that the velocity versus time relationship is velocity at any time t is the initial velocity plus ax times t. The position at time t is initial position plus vx initial t plus 1/2 ax t square, and the average velocity is basically the algebraic average of Vx initial and Vx final, and by manipulating these equations we can also see that substituting for T final, Vx final minus Vx initial over Ax, we can see that the velocity can also be written in terms of the acceleration and position as Vx final square minus Vx initial square is 2ax x final minus x initial.